right. By the way, if you're worried about grades, your test corrections are in. If you didn't get as many points as you thought you were going to, probably because you didn't give me an explanation for all of them. Does that make sense? What else? You guys done talking? I want you to talk, but like participatory. Whoa, that was a big word, and I pronounced it right on the first try. Okay. Good marker. Good marker. Let's see. Yes, that's a good marker. Good marker. No. I mean, you're probably better here for seeing, right? I just want to stay here. Okay. Do you remember? We're dealing with relating or connecting Newton's first and second laws. Do you remember Newton's first law? Physics. Absolutely. Do you remember second or third? You got one? I did what? Oh, that's okay. That's okay. I wonder if I'm better off actually to keep your attention. Can everybody see this? Yes. Okay. To keep your attention, I'm actually not going to post it until we're done with our together time. Yes?
Every action has a positive and equal reaction.
Which one's that? Second one?
I think so. I don't know.
Look, all right, hold on. Now, is it helpful maybe to remember which is which for communication purposes? Because you can say, oh yeah, that was Newton's first law, or oh, that was the second, or oh, that was the third. Does it really matter what number we put on it?
No.
What matters is that you understand the fundamentals, you understand the meaning, you understand the effect on your real world, okay? But we do have them numbered. You were describing the third, okay? For every action force, there's an equal and opposite reaction force. Does that sound familiar? Hopefully. Do you remember the first one? Huh?
I thought.
Yeah, an active force.
Yeah, that's the first one.
Inertia. Law of.
Yeah, I said it.
The law of inertia is not equal and opposite. That's third. Okay? Law of inertia is about how to change, or what it would take to change what something is doing. Okay? The law of inertia is a tendency of an object to continue to do what it's doing. If I'm sitting on the couch on a Sunday afternoon watching football, eating Cheetos, having a Diet Dr. Pepper, there's really only one thing that's going to be able to get me off my butt. The Diet Dr. Pepper. Right? Got to get up at some point. That's a potty joke. Anyway, law of inertia. Let's look at it this way. Let's think of it this way. Stuff and things and stuff, right, will continue doing what it's doing until what?
Until it's acted upon a force.
By what kind of a force?
Gravity.
Doesn't even necessarily have to be external. It has to be an unbalanced
Force.
I keep spelling words wrong today. Isn't that every day though? Unbalanced force. Okay? So things and stuff and things will continue to do what they're doing until acted upon by an unbalanced force. Good grief. Until an unbalanced force acts upon whatever the thing or the stuff is. So, let's draw a box, because that's what we've been doing lately, right? Let's draw a box. And let's give it a weight of 5 newtons. If it has a weight of 5 newtons, which direction is that force applied? Down, because what's causing it?
Gravity.
A weight is caused by gravity, so it would be toward the center of mass. Okay? it's sitting on something. This block is sitting on something. Whatever it is that it's sitting on, the ground, a table, whatever. As long as it's not sinking into it, what is the equal and opposite? So dealing with the third law right there, right? For every force, there's an equal and opposite reaction force. As long as it's not sinking, the opposite force would be what again? 5 newtons. And what would we call that force? No. Force, inertia is not a force. What is pushing back? You've got the force of gravity. Countering the force of gravity is the... No. What's that? The normal force. Somebody was paying attention a couple lessons ago. Okay, so our normal force resists the force of gravity. Okay, cool. Would we say this is a balanced arrangement? Are these forces balanced?
Yeah.
So the block's sitting there, it's not going to do anything crazy, is it?
No.
What if I have a 10 Newton force applied pushing on that way? Is it going to move now?
Yeah.
How many of y'all think it's going to move now? No. It's applied that way. Do you think it's going to move? The block, is it going to move?
Yes.
Raise your hand if you think it's going to move. You don't have enough information.
Well, literally, we don't.
You don't have enough information.
It's not rough. It might be rough. I don't know.
What's here?
The roughness.
Some amount of friction that it's going to have to overcome,
What is it called?
right? Is there such a thing as a frictionless surface?
No.
So whether it will move or not depends on how much friction's here. If our force of friction is equal to 10 newtons, it would be applied in the opposite direction, and it would cancel out. It would be a what kind of force?
Balance.
Balanced force. But if this were, say, only, well, anything less than 10, right? Anything less than 10 newtons, now it's going to start moving that way.
Okay.
Does that make sense? Because now we have an unbalanced force. It's going to make it change what it's doing. If this were already moving, same concept applies. It's already moving. Well, how could we change the movement? You'd have to have a net force to change the movement. Oh gosh, did I just use a new term? Net force? Have you heard that before? Can somebody tell me what it means, a net force? Okay. Can I erase this? Yes, no, maybe?
Yeah. You
Right.
can.
Gross and net. Those are mathematical terms usually applied to things like physics, sure, and personal finance. So I'm actually going to use some personal finance logic to help you understand the terms. How many of y'all have a job? A few of you? I mean like a job where you earn wages or tips, or how else might you earn money? Hourly wage. If you're a waitress or a waiter, maybe a tip. How about bonuses? Ooh, could we earn bonuses?
Yeah.
Like, hey, I'll pay you this much dollars per hour, but if you finish early, don't worry. I'll give you a bonus so you're still rewarded for your work. Does that make sense?
Yeah.
Have you ever heard of somebody just stretching a job out to make it take longer because they're an hourly employee?
I do
Nobody
that
would do
sometimes.
that. So maybe bonuses. Anyway, these are all types of compensation. Depending on your job, they might call them entitlements. You're entitled to this compensation. Okay? Yeah, a little bit, right? These are all positives. That's money, money, money you're going to get. Okay? You add all these together, and add them together, and you get your gross pay.
Yeah.
Does that make sense? And unless you don't make very much money, you probably wouldn't think that's gross. You're like, yeah. get some money. Okay? Anyway, net. Okay, to get net, what might be an example of a deduction from your pay? Taxes. Uncle Sam's going to get his, right?
Yeah.
How about voluntary deductions? Could you pay for your health insurance through your employer and they take that out of your pay?
Yeah.
So you could say some insurance maybe. Anyway, you got your deductions. So deductions would be what out of your compensation? What kind of math operation would we be doing?
Subtracting.
We'd be subtracting, right? So we got our positives here, we got our negatives here. So we would subtract it out and you end up with what you're left with. What's left is your net. Your net pay. So you have your gross pay, all the money you're given, but then you got to subtract out your deductions, and what you're left with is your net pay. Aww. There's a bug in my coffee. Oh, no, I swam to the other side. No! You don't believe me, it's in there. All right. Are we good on that? So, net. So if the pushing force was this way with 10, and the friction force was that way with 5, what's the difference? 5. Right? And if you're, depending on which way you label as positive or negative, 10 minus 5 is 5, not negative 5. It just depends on the way you're looking at it, right? So, how about, can I erase this?
Yeah.
Or maybe just start over here. How about the second one? This is the one that a lot of people forget because it's usually not represented with words. It's represented with what?
Force equal to mass times acceleration.
Usually represented with variables, right? Force equals mass times acceleration. So this is, Newton's second law is about relationships. What is the relationship between force, mass, and acceleration? Well, the amount of force it takes to accelerate a certain object of a certain mass depends on multiplying those together. So if you want to accelerate a vehicle at a certain rate, you take that rate of acceleration times its mass to get how many newtons of force it will take to do that. And then of course you can take that force, put it in a little calculator, a little formula that I'm not going to give you, I don't think, and you could say, well, how many horsepower, or what's the torque necessary to accelerate that quick, right?
337 horsepower.
All right, so does it show it to you in another way? I haven't assigned it yet, so you don't know. Right there. So Newton's second law can be summarized this way, and then it says, or more commonly, force equals mass times acceleration. Well, then why did they put this here first? You can.
They want to confuse you.
They want to confuse you? No, I don't think so. That's not what they're trying to do. That might happen, but that's not what they're trying to do. Let's work one. Let's say you're trying to find force. No. Let's say you're trying to find acceleration. Okay. This would be convenient, wouldn't it?
Yeah.
This formula, A equals force, acceleration equals force divided by mass, is designed so that you do one step and you're done, right? But if you're, old-fashioned perhaps, or you can't remember all the formulas, can I find acceleration with that formula?
Yes.
Let's just demonstrate. Most of you, I think, know this, but let's demonstrate. Are you okay? What's funny? I like jokes.
Me too, guys.
What kind of sound was that? It just came out of your mouth. Like, All right. So let's say we have a force of 10 newtons, and we have a mass of 2 kilograms. We'd be looking for an acceleration with what kind of units? Acceleration is measured in what kind of unit?
Meters per second.
Acceleration is a change in velocity. What is acceleration measured in?
Meters per second. Square.
Squared, there we go, because meters per second is just velocity, right?
Yeah. Yeah.
Actually, meters per second is just speed,
Yeah. Yeah.
right?
That's what I was thinking.
So we're looking for meters per second squared, question mark. Okay, cool. So somebody tell me what would go where in that formula. All you gotta do is plug it in. What would you plug in there? Take these things and put them in there. What would go for force? 10 newtons, because force is measured in newtons. So we're going to go ahead, we're going to use this formula, we're going to rewrite it, inserting the things for the things and the stuff. So for force, we're going to write 10 newtons. We're going to say that's equal to, somebody else, tell me, what do I put next? Welch. The 2 kilograms, the mass, because it tells me right there, that's what I put in next. And then we're going to be multiplying by acceleration, but we don't know what that is yet, so we're just going to leave it A. What do I do next? Go.
10 divided by 2 or whatever. 2.
What am I doing at the same time that I'm dividing 10 by 2? I'm isolating the variable, and to isolate the variable, I have to divide what by 2? 2 by 2. So the first thing I'm doing is I was saying, I got to get this out of here so that A is by itself. So I'm going to divide 2 kilograms by itself. When I do that, what am I left with?
A.
Times 1.
Yeah.
Because this becomes a 1. But I don't need to write the 1, do I?
No.
Because whatever A is times 1 is just
A.
A. So, but if I did it to one side, I got to do it to the other. 2 kilograms dividing 10 newtons gives me
5 and 10.
5 newtons?
5 kilograms.
5 kilograms? Mayfield, what are we looking for?
Oh yeah, meters per second.
Hold on. But what if we didn't remember that? What if we didn't remember that? I want you to think back. What's a newton? Not the delicious fruit, like nougat little cake thing. Not fig newtons. Newtons are what? It's force measured with what units? 1 newton is equal to 1 kilogram times, guys, force is equal to mass times acceleration. 1 newton of force is equal to 1 kilogram of mass times what? How much? 1. 1 newton equals 1 kilogram times 1 meter per second squared of acceleration. So could I rewrite, to help me figure out what my unit's going to be, could I rewrite newtons as something else?
Yes.
What would I rewrite it as? kg what? Kilogram. It's kilograms times meters per second squared. So 10 kilogram meters per second squared is the same as 10 newtons. They mean the same thing because newtons are kilogram meters per second squared. So look what happens. When we divide it, the kilograms get divided out. What's the only unit left? Make sense? I love it. All right, cool. Now, but what did we just do then? What's 10 newtons? force. And what's 2 kilograms? Mass. And what's this over here again?
Acceleration.
Isn't that just written in reverse?
Yes.
So the only reason I did that is just to show you that this is equal to this. They're just laid out differently. Here you're just isolating the variable before you start. You're rewriting the formula. This is equal to that. Mathematically, they mean the exact same thing. They're just written in a different way. This one we're wanting to solve for acceleration if we're given these two. This one we're trying to solve for force if we're given those two. Okay? They mean the same thing. All right, so that's Newton's second law mathematically. Did I already do an example of 2 things, different mass? You guys? Did I? Football? Did I do the football analogy?
No, you have not.
All right, so I'm going to look. Let's look at this force equals mass times acceleration thing without numbers to help with understanding. We're going to look at it without numbers. Okay? Could I have who's usually the smallest football player on the field? Running back?
The kicker.
Could you have a pretty big running back? I mean, come on.
Yeah.
Do you remember King Henry? Right? Remember King Henry? He's a pretty big running back, isn't he? Who's kicker? I've seen some big kickers. You don't have to be small to be a kicker. You know what kind of players usually like pretty small? What position? Safeties are usually pretty small. Wide receivers are usually tall. What about the inverse of the wide receiver?
Quarterback.
Cornerback. Not quarterback, cornerback. A cornerback is the defender opposite the wide receiver. It's their job to stop the pass from getting received. Does that make sense? So the receiver goes out for a pass, they try to catch it, the cornerback's trying to knock it down or intercept it, right? And they're usually the smallest, consistently the smallest people on the field. Who's the biggest? The lineman. Guard or tackle? Tackle, because the guard sometimes does what? Sometimes they pull. So they have to be able to move, right? So they're usually not as big as the tackle, at least on offense. Right? So check this out. Force is equal to mass times acceleration. What if I were to tell you that the force exerted by a cornerback could be the same as the force exerted by the lineman?
Makes sense.
Huh? How might that work with our mass times acceleration? Go.
Because, like a D lineman, they have a lot more mass.
Okay, so let's do lineman first. So the lineman would have more mass
And less acceleration.
because they can't get up to as high of a velocity, right? So when they slow down, they're not doing it as quickly. They're not doing it from as high of a value, right? Because they can still slow down pretty quick if they hit something, right? Okay. What about the cornerback? Wouldn't it be the inverse of that?
Yes.
So the acceleration is going to be more, and the mass will be less. So let me put it to you this way. I'll do it another way. Does that make sense, by the way?
Yeah.
So the cornerback can get up to a higher speed. He's smaller. He's got less mass, but he can get up to a higher speed. So when they impact, there's more acceleration because he's going faster. From faster to zero is more acceleration than slower to zero. Does that make sense? So you can produce the same amount of force. Okay. Yeah.
So so the cornerback just needs more acceleration so he can move faster, but less mass. So it's like.
To produce the same amount of force,
Yeah.
he'd have to get up to more speed. Let me put it to you this way. Let's say, who's the smallest person in here?
Me.
Dude? Welch? I don't know. You look pretty tiny over there on the end. Real dainty. We got a couple small people in here. All right, so who's the biggest dude? You? Okay, are you the biggest one in here? Probably. Okay, what do you weigh? What do you weigh? What do you weigh? It is a personal question. What do you weigh?
Yeah.
About what?
About 225.
Really?
Yeah.
Stand up.
Big old boy. A lot of muscle on you. That's more than you.
All right, hold on.
I squat 500. I'm down.
I'm a little taller, but muscle weighs more than fat, right?
Yeah.
Squish, squish. You gonna flex? Oh, you're squishy there too. Okay. Anyway, he does. Did I touch you on your back? You got a little bit of muscle there. Okay. So 225.
Yes.
That's about what I weigh. All right. So imagine Kea or I tackling. I'm sorry. What's your name? Imagine Kea or I. And may I ask you your weight?
Yeah,
What is it?
like 98.
98 pounds. So either one of us, okay, you're a little stronger. So we're gonna say Kea. Emerson is just walking along the sidewalk, minding her own business. Let's say she's reading a book while she's walking, or do you have a phone that you like to look at while you're walking? You're terrible. So let's say she's just minding her own business. She's walking on the sidewalk. She's flipping through like YouTube shorts or something, or TikTok videos, or whatever it is. And Kea, I don't know what his motivation is, but he just comes at her full speed and drives his shoulder into her. Spear tackle. You know what I'm talking about? Spear tackle, right? Totally lays her out. All right, hold on. Yep. All right, shh. I've got a question for you. What body part is going to experience more force on impact? His shoulder into her stomach, or her stomach into his shoulder?
His shoulder first.
Her stomach. The opposite.
Her stomach's good.
Hold on now. We started, you guys wanted to give me Newton's third law first.
What was it?
Oh, force, active
So let's put number 3 up here.
Wait, we're doing it there?
For
force.
every
Motion until acted upon.
for every action force, in this case the action force would be his shoulder impacting her stomach. For every action force, there's an equal and opposite reaction force. So, who's going to have more force impacting them? Kea or Emerson?
Emerson.
Guys!
Emerson.
I'm having a really hard time understanding
Equal
this.
and opposite.
Bro, it's Emerson.
His shoulder will have the same amount of force impacting it as her stomach has impacting it.
You tricked me. That's what I wanted to say first.
You wanted to see it really accurate.
Now, what you were thinking is, which one's getting the worst end of that force? Which body part is probably capable of taking more impact? A football player's shoulder, or just some random person's stomach that wasn't even expecting it? That random person's stomach that wasn't expecting it. So the pain might be on one end or another. Think about what can absorb the force better, right? If you're laying out into tackling somebody, that force is going to be transferred down pretty solid structures through the body. But on the receiving end of it, if you're getting hit in the stomach, is there as much resistance there to the force?
Oh, not unless you're just going really strong.
But the force is the same.
Yes.
What?
Would that be the same thing for like shooting like a bullet at like a wall or something?
Yes. So, another good example. So for the third of Newton's laws of motion, equal and opposite, right? Has anybody ever fired a weapon and they felt the recoil? So you've got it up on your shoulder, you fire it and it kicks, right? It hits you. So the amount of kick it gave you is going to be the same as the bullet feels. The force that is exerted upon you is going to be the same as the force exerted upon the bullet that propels it out the barrel.
I basically got shot.
Okay? But what's the difference? It's the same amount of force, but the bullet, it's applied to a very small, depending on the caliber round, right?
So it doesn't hurt that.
Where your stock of your weapon is distributing that force over a large area on your shoulder. Right? Good example. Okay. All right. So where are we? Well, what have we done? What do we need to do still? We covered first law, we covered second law, we covered third, which we're not even there yet. We actually worked one of these examples. What I'm going to do, I'm going to turn you guys loose. You got a little bit of time left, okay? There's 2 or 3 videos to watch. There's a couple of simulations to do. And if you want to do any reading or note-taking, by all means,